This is the Chem 1 lesson over the second half of heating calculations. So we're going to do heat calculations involving phase changes and then putting it all together with a heating curve. So previously we talked about how to handle calculating heat when there was a temperature change, right, which is our diagonal lines on our heating curve, but we have not yet talked about what to do when there's a phase change. We can't use MC delta T because we don't have a change in temperature. So we do need a different equation. So these guys look a little bit different. Both still have heat, Q, right, that's going to be in joules. They both still have mass, it depends on how much of it you have, but then there's two new constants. You have HF and HV. HF stands for the heat of fusion, right? It's how many joules per gram it is to either melt or freeze something, depending on whether you're adding or removing heat. And the second one, HV, has to do with the heat of vaporization. It's the same unit, joules per gram, but it has to do with how much energy it takes to vaporize or condense a gram of that substance. Again, whether we're adding or removing heat, look a little bit different. So let's talk about these constants a little bit more. The heat of fusion, again, that has to do with melting, really. So it's loosening intermolecular forces, right? We're going from a solid where they're really tight to a liquid where it's a little bit looser. So we're talking about melting a substance. The heat of vaporization is the heat used to break intermolecular forces. When something goes from a liquid to a gas, you have to remove IMFs. So think about that as the heat energy required to boil something. So which one do you think's harder to do? A loosen intermolecular force or break one? Well, breaking is going to require more energy. So therefore, HV is going to be a higher value. So if you're looking at HF and HV, HV is going to be bigger, which also means that line of the heating curve, that vaporization line, actually if it's drawn to scale, which I'm usually not drawing them to scale, should be longer than that melting line because it takes more energy to break those intermolecular forces than it is to loosen it. So let's look at some examples. How much heat must be added to 75 grams of water at 100 degrees to boil it? So the key word here is boil. We're talking about a phase change. 100 degrees, I know water is already boiling, so we're not changing a temperature. That energy is going into breaking intermolecular forces since we're going from a liquid to a gas. So I know my equation is going to be Q equals mHV. So we're trying to find heat. Q is what we're looking for. We're given that we have 75 grams. Now HV, we're looking at water, so you're going to have to look that up. You've got a big list of constants in your notes there. We're looking for HV for water, so heat of vaporization for water is 2,260. It's a pretty big number there. Joules per gram. You multiply those numbers out, and you're going to get really big number, 1,69500 joules. That's how much energy it takes to boil 75 grams of water. One problem where we were dealing with that boiling flat line, Q equals mHV. Now the next one, we're still dealing with water, right, because we see that it's ice. So if you think about your heating curve, I know 0 and 100 are going to be those temperatures that we melt and freeze. And if we're talking about melting, I know we're talking about a phase change, right, and melting is that bottom flat line there. And this time, so Q equals, in this case, mHF, since we're dealing with melting. And we have joules, so we know 1,500 joules is going to equal, we don't know mass, times HF. The HF for water is 334 joules per gram. Since we're trying to find mass, we're going to have to divide both sides by 334. So we're going to divide 1,500 by 334, and we're going to get 4.5. Now let's think about those units. The joules are going to cancel out. We're left with 1 over grams, so it flips around and turns into a numerator unit of grams, which is the appropriate unit for mass, so we know we did the algebra correctly. So now we did a problem where we're dealing with melting, that's that bottom flat line, Q equals mHF. Let's put all those formulas into the heating curve. So quick recap, anytime we're dealing with a diagonal line, we're going to use Q equals mc delta T, because that heat energy is going into changing that temperature. Then, anytime we're dealing with a flat line, right, we're doing a phase change, we're going to need to use the two equations using a phase change. So whether it's Q equals mHF if we're dealing with freezing melting, or Q equals mHV if we're dealing with vaporization or condensation. So to know which equation to use, you need to think about where you are in a heating curve. Are we talking about a temperature change, or are we talking about a phase change? But typically one happens or the other, unless multiple things happen, then you're going to have more than one equation. So if you look at this next example, it's a little bit different. In this problem, we're asked to find heat, so we're trying to find Q. We've got 5 grams, so we know our mass. We've got a temperature change, right? Negative 5 degrees Celsius to steam at 152. But if you think about where we are here, we're going from negative 5 all the way down into the area that's a solid, all the way up to 152 degrees, which is way up here with steam. So we're actually starting as a solid, and we're going all the way up to a gas. So here we're going to be going over multiple steps in the heating curve. Each line is going to be a different formula. So we essentially have 5 different parts. I'm going to letter them. So down here, that first diagonal line, that would be A, right? That's where we're going to have to take that solid, bring it up to the melting temperature. Then we're going to have B, that's our phase change. That's where we're going to melt that ice. C formula is going to be where we're going to heat up that water to the boiling temperature. D then is going to be the actual boiling or vaporizing, but then we're not quite done yet because then we have to bring it, now it's going to be 100 degrees, but we have to bring it up to 152, so we're going to have to vaporize it, heat up the steam, it's already vaporized. So we're actually going to have 5 equations here, so give yourself plenty of room. So we said at letter A that we were changing the temperature, so we're going to use Q equals MC delta T. We're going to plug in those values here. So let's see, our mass is going to be 5 grams times the specific heat. We're going to have to look that up on your list of specific heats. And we're dealing with a solid here, so you have to pull the specific heat of solid water, which is 2.06 joules per gram degree Celsius, times that change in temperature. Now what's important here is we only want the change in temperature of that tiny little piece of A on the graph. So final minus initial is going to be 0 minus negative 5 degrees Celsius. So our change in temperature here is only 5 degrees Celsius. I'm not interested in the change in temperature of the whole thing, right? Because on that part of the graph, we're just going from negative 5 to 0 degrees. So it's just a 5-degree change. So when you multiply those guys out, you're going to get, let's see, 5 times 2.06 times 5 is going to equal 51.5 joules. So that right there is going to be the amount of energy it took to get that ice cube to 0 degrees, to get it to start melting. We're not done yet though. We need to do equation B. So to equation B, let's see, it's a flat line, and we're between a solid and a liquid, so we're going to have to use Q equals MHF, plug those values in, 5 grams times the HF of water, so we have to look up the heat of fusion of water. You're going to get that it's 334 joules per gram. Multiply that out, so 5 times 334 is going to give you 1,670 joules. So that's how much energy, it's ugly, it takes to melt that ice. Now we're going to have to keep going. So in step C, we got another diagonal line, so we're going to have to use MCAT again, but this time we're dealing with a liquid. So it's still 5 grams. We have to pull the specific heat of liquid water, 4.18 joules per gram degree Celsius, times this change in temperature. The change in temperature for step C, the final is 100 minus the initial of 0. So here that temperature changed 100 degrees Celsius. Multiply that out. 5 times 4.18 times 100 is going to equal 2,090 joules. So now we've got 3 out of the 5 steps. Got to keep going. So now, let's slow this down a little bit. We're going to go with step D, which is a phase change. It's flat. So we're going to have to use MHV here. So our mass is still 5 grams times HV for water. You'll have to look that up in your notes. The HV for water is 2,260 joules per gram. So we have to multiply those numbers. 5 times 2260 is going to give us 11,300 joules. So we're getting closer here. That's the heat energy it took to vaporize that 5 grams of water. Now we have the one last step, which is step E. We have another diagonal line. So we know it's going to be an MC delta T. Call that MCAT. So 5 grams times, now this time we have to use a specific heat of steam, right, of gas water. So that's 2.02 joules per gram degree Celsius times that change in temperature of just step E. So final would be 152 minus the initial, which we started at 100. So it's only a 52 degree change. Multiply those guys out. 5 times 2.02 times 52 is going to give you 525.2 joules. Now notice I haven't worried about sig figs yet because we have not gotten our final answer. So now I have all 5 sets of joules for each individual part of the equation. So the tricky part now is we need to add them all together. So to find that total heat, I'm going to have to take my 51.5 plus the heat in B, so what was that, 1,670 joules, plus C, 2,090 joules, plus D, 11,300 joules, plus our last one, 525.2 joules. We add them all together, and we get our total number of heat energy, which is going to be 15,636.7 joules. Now, in a problem like this, we're not going to expect you to round to sig figs because we've now subtracted. That has one rule for sig figs, and then we've had you multiply, which is a different set, and then add them, different set of rules. We're not going to worry about sig figs here. I usually just report it all out, however the calculator says. So there you have it. We've gone through all 5 steps of that heating curve. So step A, we were heating up that ice to its melting point. Step B, we were melting that ice, turning it all into liquid. Step C, we were heating up that liquid up to the boiling point. D was taking that boiling water and vaporizing it onto steam. And step E was heating up that steam up to 152 degrees. Our next example is asking about 98 grams of steam at 100 degrees cooled to water at 25 degrees. So I sketched out my heating curve. I know it's water, so I put in my melting and boiling at 0 and 100. Now let's think about where we are in this heating curve. We are at 98 grams of steam at 100 degrees. So steam at 100 degrees would be the top, our flat line. Before it's steam, we're right here. And then we're cooling it down to water at 25 degrees. So 25 degrees would be, I don't know, about right there. So we're not going across the whole heating curve. We actually have 2 different lines we're dealing with. Also keep in mind that we're actually going to the left on this guy. This is actually an exothermic reaction. This thing is cooling off. It's losing heat energy. Honestly, the easiest way to do this calculation is we're going to do the heating curve like it was endothermic, gaining heat energy. So we're actually going to do the calculation going from 25 to steam at 100 degrees, and to show that it's actually the heat's going the opposite direction as being released, we're just going to make that sign negative at the end. You can change the signs along the way, but it gets a little confusing because you need to end up with negative numbers of joules. By the changing in temperature, it gets a little tricky, and then you have to flip the sign of HF or HV if you're using it. So we find that it's easier just to work it out endothermically, gaining heat energy, flip the sign at the end. So we've got 2 equations here. I'm going to label them an A and a B. So at step A, it's a diagonal line, so we're going to have to use MC delta T. Our mass is 98.0 grams. Specific heat, we're dealing with water as a liquid here, so our specific heat's going to be liquid, 4.18 joules per gram degree Celsius. And that change in temperature is going to be just for that part of the graph, so final, which is 100 degrees Celsius, minus the initial, which was 25. You guys can probably do that math. That's actually just 75 degree change. So you multiply those numbers, so 98 times 4.18 times 75 is going to give you 30,723 joules. So that's just for the first step. Now step B is going to be, or we're going to do it as a vaporization. It is condensation actually, but we're going to work it out like it's gaining heat energy. So that's going to be Q equals MHV, our 98.0 grams, times HV for water, which is 2,260 joules per gram. Multiply those guys out, 98 times 2260 is going to give us 221,480 joules. Very large number there. So we've got our two numbers of joules for our two parts of our graph. We do need to add them together, and don't forget we need to flip the sign. So to find our total heat, we're going to have to take our two numbers, 30723 joules, plus our 221,480 joules. Add those guys together. You're going to get a really big number. You're going to get 252,203 joules. Now keep in mind, since this is exothermic, we're going to need to make that sign negative to show that it is losing heat energy. We're actually releasing that much heat energy out into the environment. So this problem was a little bit different. We were releasing heat energy, so it's exothermic. We still worked it out in the endothermic direction, so gaining heat energy. We had to use MCAT to heat up that water to boiling, and then we had to boil that water into steam. So we had two parts of this graph. We had to add it together and then flip the sign because we actually are releasing that heat energy. The last example is finally not water. We're now dealing with silver. So we've got 75 grams of silver, and we're going from 900 to 1,005 degrees. So our heating curve looks a little bit different. The steps are the same, but the temperatures are different. We don't have 0 and 100 degrees because this is not water. All I did was I took the boiling point and the freezing points that were given to me, and then I put those in as my flat lines. So now let's think about on this graph where we're going here. So we're going from 900 to 1,005 degrees. So we are going from 900, which is going to be down here, to 1,005, which is just above here. So we are going from here to here. So that's going to be 3 steps. We're going to have an MCAT, and then we're going to have an MHF, and then we're going to have another MCAT here. So we're going to have 3 different equations. So, and we've got all those constants listed for us in the problem because these guys are a little bit different. Let's get going on this. So step A is going to be MCAT. Let's plug those guys in. 75 grams times the specific heat of silver. Now this time, if you look at step A, we're dealing with solid. So we're going to have to be sure we pull the solid specific heat, 0.187, times its change in temperature. Now be careful, we don't have those nice numbers of 0 and 100 for our melting and boiling here. We have 961. So for step A, the final would be 961 degrees Celsius minus the initial of 900. So it ends up being 61 degree change. Multiply those out, so 75 times 0.187 times 61 is going to give us 855.525 joules. Okay, step B is going to be a phase change. We're melting, so MHF, so we're going to have our 75 grams times our HF, which were given to us in the problem, which is 88, dropping units, times 88 is going to give us 6,600 joules. So we've got our second one. Now we just have to do our last one. Step C is going to be another MCAT. So we still have 75 grams. Now be mindful, the specific heat we need to use here is for liquid. So you've got to pull the 0.233. Now this change in temperature is going to be our final 1005 minus where it started, which is 961. So 1005 minus 961 is going to give you 44 degree change. So you need to multiply these guys. So 75 times 0.233 times 44 is going to give you 768.9 joules. So now we need to add these three guys up. So we've got the 855 and the 6600 and the 768. You add them all together, and you're going to get 8,224.43 joules. So there you've got it. So we've done a heating curve where we had all 5 steps, where we went from solid to liquid to gas. You saw one where it was exothermic, so it was releasing heat energy. We still worked it out forward, flip the sign at the end, and now you've seen one where we only went over 3 steps and it was not water, so it made those changes in temperature a little bit more tricky.